to 14.4 now, and we're going to talk about equations of tangent planes and linear approximations. And like I said, this goes hand in hand with partial derivatives, so I kind of already talked about this. This was the Calc 1 application of linear approximation, where we would say, okay, in Calc 1, you have a curve, and we would find a tangent line to that curve. And again, the idea was that the equation of the tangent line can help us approximate a value that we want to know that's really close to a value that we do know. That was the Calc 1 approximation, or the Calc 1 application. In Calc 3, we don't have curves anymore. What do we have? We have surfaces. So imagine this being something that's more three-dimensional. So imagine instead of just like the square root function, maybe you have something that looks more like a dome. Again, you don't need to write this down necessarily. So you would have something that kind of looks like this. I know I'm great at drawing. And then you don't have tangent lines anymore when you're in 3 dimensions. What do you have instead? Tangent planes. So this would be a tangent plane instead of a tangent line. And that's the idea. Same thing we did in Calc 1, except we're going to use a tangent plane instead of a tangent line. So that kind of begs the question, how do you find the equation of a tangent plane? You're going to use this formula right here to use the equation of a tangent plane. Now, we're going to end up doing this twice in chapter 14. There's going to be 2 different times where we find the equation of a tangent plane, and it's going to seem as if we're doing 2 completely different things. And in a way we are. What I want you to focus on right now is that we are finding the equation of a tangent plane to a surface that's explicitly defined as z equals some function of x and y. So it's something where you have z equals, and it is explicitly defined. In other words, your z's are not all jumbled together with your x's and y's. You have to treat that differently. We'll deal with that later. Okay, this is the formula you're going to use. So what we need to do is we need to find the partial derivative with respect to x and the partial derivative with respect to y at the given point. Let's do an example. All right, this one here says find the equation of the equation of the tangent plane to this surface at the point where x equals 1 and y equals 2. Okay, the first thing that I want to do is I want to find out what this c value is. So in other words, when x is 1 and y is 2, find c by plugging in a and b. Okay, so that's what I'm going to do. So the first thing I'm going to do is I'm going to say that at the point 1, 2, z equals 5 times 1 squared, which is 1, times the square root of, if we plug in a 2 here, 2 cubed is 8, 8 times 2 is 16, 16 plus 9 is 25, square root of 25 is 5, 5 times 5 is 25. So overall, we get 25 for our z or our c value. So we're dealing with the point 1, 2, 25. So this is what is going to act as my A, B, and C in that formula up above. Now what we want to do is we want to take our partial derivatives. So given this function right here, we have z equals, we could also consider this our f of xy equals. So remember, this is z as a function of x and y, so you can see it like that as well. So if we want to take our partial derivatives, I'm going to start by taking the partial derivative with respect to x. Now remember, if you take the partial derivative with respect to x, this means x is your variable and y is your constant. So the derivative of 5x squared is going to be 10x, and that whole square root term is just a number, so he just comes along for the ride. Now, if you take the partial derivative with respect to y, in this case, that 5x squared is just a number. And then if you have the square root of something and you take the derivative, it's going to be 1 over 2 times the square root of that thing. So that would be 1/2 times this guy to the negative 1/2. And then chain rule says you need to multiply by the derivative of the inside. So the derivative of 2y cubed is going to be 6y squared. Okay. So now, if you want to, and I know I went through those partial derivatives a little bit quickly. If you have questions on how I did that, you can always email me. But for the most part, people are okay taking the partial derivatives. It's the concepts behind what we're going to do with them after we take them that throws people off. So what I'm going to do now is I'm gonna find what my partial derivative is evaluated at an x value of 1 and a y value of 2, because I'm trying to find the equation of the tangent plane at that specific point. So if I plug in a 1 for x and a 2 for y, that's going to give me 10 times 1. And then when we plugged the 2 into that square root, that gave us square root of 25, which was 5. So that gave us a 50 overall. And then here, if we plug in, let's see, we have 5 times 6, which is 30. Then if you plug in a 1 for x, sorry, let me write down what I'm doing. We're plugging in a 1 too. So that gives us 30. If you plug in a 1 for x and a 2 for y, and that was a 5. Okay, so let's see. This is going to give us 30 over 5, which is 6. I probably did not do this in an efficient way. 6 times 4 is 24. 24 divided by 2 is 12. However you decide to do that, arithmetic is not my greatest skill set here. It's funny because all my friends think I'm really good at math, and to be fair, I am. But for the longest time, I was always like the assumed tip calculator when we would go out to dinner. Like, oh, you're good at math, you calculate the tip. And I'm like, no, you don't understand. I can take derivatives and really complex integrals, can take partial derivatives, calculate 20% of something. That's not my wheelhouse. All right, anyway, aren't you glad to know that the person that you are learning math from doesn't know how to do arithmetic? It's a different part of the brain, I'm convinced of that. In any case, we have everything we need now, so we're going to plug into that formula at the top of the page. So that formula for the equation of a tangent plane is z minus c equals your fx, your partial derivative at your point, times x minus a, plus your partial derivative with respect to y at your point, times y minus b. So just copying that from the top of the page, plugging in everything we know, that's going to be z minus 25 equals our partial derivative with respect to x at our point, which is 50, times x minus our a value, which is 1, plus 12 times y minus 2. Now, simplifying this down a little bit, that's going to give us z minus 25 equals 50x minus 50 plus 12y minus 24. Getting all of our constants on one side and variables on the other, we will subtract that z over, and then we have minus negative 25 plus 50 is going to give us positive 25. Positive 25 plus 24 is going to give us 49. So this would be how the equation of the plane looks overall. Back. All right, so all of that is to find the equation of a tangent plane, and just like in Calc 1, how we could use the equation of the tangent line to approximate values, we can do the same thing in Calc 3. We can use the equation of the tangent plane to approximate values on a surface. Now, they give you this linear approximation formula here as if it's something completely new, but this linear approximation formula here, this guy, is the same thing as the equation of a tangent plane, right? Instead of calling it a z, they call it an L of xy, and instead of calling it a c, they call it an f of ab and move it over to the other side, but it is the exact same thing. So don't let the notation confuse you. All this is the equation of a tangent plane. What we're going to be doing now, instead of just finding it, is we are going to use it to approximate values. This would be your linear approximation formula if you have a function of 3 variables instead of 2. We'll get into that in a minute. Let's do an example. Find the linear approximation of this function at the point 0, negative 1, and then use it to approximate f of this guy right here. Okay, this is really 2 questions snuck into one. This is find the linear approximation of this function at this point. That's going to be step 1. And then use it to approximate this value. Let's go ahead and do that. The first thing that we want to find is we want to find f of 0, negative 1 by plugging in a 0 for x and a negative 1 for y into our function. So that's going to give us negative 1 e to the 0, which is 1, over 0 squared plus 4, so negative 1/4. right? And now what we need to do is we need to find our partial derivatives with respect to x and with respect to y. So if we want to find our partial with respect to x, in this case, we're going to have to use a quotient rule because we have x's on top and x's on bottom. So to use the quotient rule, it's going to be bottom left alone times the derivative of the top. Now we're taking the derivative of the top with respect to x, so we're treating y just like a number. So the derivative of e to the 2x would be 2y e to the 2x minus top left alone times the derivative of the bottom, which is 2x, all over the bottom squared. Okay, so that's our partial with respect to x. Let's take our partial with respect to y. And again, don't worry about simplifying this. We're going to plug in a number into this, so you don't want to waste your time simplifying. If we take the partial with respect to y, this is a little bit easier because we only have one y in our function, so everything else is just acting like a number multiplied by that y. So its partial derivative would just be e to the 2x over x squared plus 4. That's all just some fraction times y. All right, so we'll take our partial derivatives and we'll plug in our point. So we're going to plug in a 0 for x and a -1 for y. So if you do that, if you plug in a 0 for x, that's going to give us 4 times 2, a y value of -1. E to the 0 is going to be 1. This whole term here is going to drop out if you plug in a 0 for x. And then on bottom, we have 0 plus 4 is 4. 4 squared is 16. So we have -8 over 16, or -1/2. And then over here, if you plug a 0, -1 into your partial with respect to y, if you plug a 0 in for x on top, e to the 0 is 1. If you plug a 0 in for x on bottom, 4. Now we have everything we need. Instead of finding the equation of the tangent plane, this time we're finding the linear approximation. So we're using a slightly different notation here. So we're going to say that L of xy equals our f of AB, which is -1/4, plus our partial with respect to x, which is -1/2, times x minus a, plus our partial with respect to y, which was 1/4, times y minus our b, so y plus 1. If you want to simplify this down a little bit, we can write that as -1/4 minus 1/2 x plus 1/4 times y plus 1. In general, I don't like distributing these numbers and then adding like terms together. I think this is going to be easier to plug into given our values up here. With that being said, if you want to simplify this, like I'm looking at this and I'm seeing, okay, well, if I distribute that 1/4, then I'm going to get these 1/4 that cancel out. If you want to do that, you can. But in general, for the most part, these are set up in such a way that plugging in as is without distributing anything is generally going to be relatively easy. So this is our linear approximation formula. So what we're going to do is we're going to use that to approximate f of 0.1. Whoops, let me try that again. All right, so we are going to use this to approximate f of 0.1, comma, -1.2. And we're going to do that by taking our formula and plugging in a 0.1 for our x and a -1.2 for our y. So when we do that, we get -1/4 minus 1/2 times 0.1 plus 1/4 times -1.2 plus 1. So that's going to give us -1/4 minus, you can choose whether you want to work in fractions or decimals. Let me make sure I'm not writing over, or make sure I'm not standing over my writing. You can choose whether you want to work in fractions or decimals. I tend to prefer fractions, so I'm going to go that route. I'm going to convert that 0.1 into a 1/10 plus 1/4. This guy right here will be -0.2 inside of there. So 0.2 would be 2/10 or 1/5. So that's going to give us negative 1/4 minus 1 over 20 plus 1 over 20. So overall, that gives us negative 1/4. That does not sound right. Let me make sure I didn't screw something up. Yes, this is negative. Let's go back a second. That's supposed to be negative. I told you guys, arithmetic and negatives, we don't get along. All right, so if we wanted to get a common denominator here, we would need to multiply that, and that would be times 5, so that would be negative 5 over 20 minus 1 over 20 minus 1 over 20. We should get negative 7 over 20 here as our final approximation. Now, what you get as your final answer here should be relatively close to your f of 0, 1 that you started with, okay? Because what we're doing is we're using f of 0, 1 and the derivatives, the rates of change around f of 0, 1 to approximate something really close to f of 0, negative 1. So those values should be relatively close together. So I had negative 1/4 here, which is like negative 0.25. 7 over 20 would be 3.5 over 10, so that would be about 0.35. So comparing negative 0.25 to negative 0.35, those are pretty close together. Chances are we did this correctly, assuming my arithmetic skills were right. If you got something like negative 1/4 here and 82 as your answer here, you might be like, wait a second. Just increasing my x's and y's by that amount made me go from negative 1/4 to 82. Something doesn't seem right there. You might want to reevaluate.